We're looking at Chapter 3, Section 3.6, Solve Problems that Involve the Probability of Two Events. In this lesson, we will look at distinguishing between independent and dependent events, and we'll use conditional probability to calculate the probability of dependent events. Let's recall mutually exclusive and non-mutually exclusive. If two events are mutually exclusive, then they are disjoint. The probability of mutually exclusive events is the probability of A plus the probability of B. In non-mutually exclusive, this is where there are elements in common. There's an overlapping region. And the probability of A union B in non-mutually exclusive events is the probability of A plus the probability of B subtract the intersection. Let's recall probability is the ratio of favorable outcomes to the total number of outcomes. That is, the outcomes that we want that are favorable to A, the event that we're looking for, over the total number of outcomes possible. Independent and dependent events. So we have to look at first the difference between independent and dependent events. Independent events, if the probability of event B occurs and it does not depend on the probability of event A occurring, then the two events are said to be independent. That is, event B does not depend on the probability of event A. Dependent events. If the probability of one event depends on the probability of another, then these events are said to be dependent. So let's look at some examples. Independent or not. Independent or dependent, rather. Event A is rolling an even number on a die. Event B is choosing a marble from a bag. These events are independent. Since one event, the probability of event A does not depend on event B, or event B does not depend on event A. Let's look at another example. Event A is choosing an ace from a deck of cards. Event B is choosing a king from the same deck without replacing the first. Without replacing. That's key here. This is dependent events. Since the event B, the probability of event B, does depend on the probability of event A. Event A is choosing an ace from a deck of cards. Event B is choosing a king from the same deck after replacing the first card. This is independent. Event A is rolling a 3 on a die. Event B is rolling a 5 on the same die. Once again, this is independent. Since the probability of getting the 5 does not depend on the probability of getting the 3. So for independent events, we may draw a tree diagram to observe the outcomes for two independent events. For example, rolling a die and flipping a coin are two independent events. Looking at this, we can see that there are, for each number that we roll on a die, there are two possible outcomes. That gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible outcomes. What is the probability of rolling a 3 and a heads? Since there's 12 outcomes in total, of getting a 3 and a heads, there's only one option. So the probability of getting a 3 and a heads is 1/12. That is the probability. What is the probability of rolling an odd and a tails? So the probability of rolling an odd and a tails, there are 1, 2, 3 odd numbers. So the odd and the tails would be 1, 2, 3. 3 options out of the 12. Which gives us 1/4. We can see that the probability of 2 independent events occurring, so the probability of A and B occurring, is the probability of A times the probability of B. Let's just go back to look. So if we look at the probability of rolling a heads and a 3, the probability of rolling a 3 times the probability of rolling a heads. Sorry, the probability of flipping a heads. The probability of rolling a 3 will be 1/6 times the probability of rolling a heads, which would be 1/2. That gives us the 1/12. The probability of rolling an odd number would be 1/2 times the probability of rolling a tails, which is 1/2, gives us the 1/4, which we've seen in the tree diagram. So let's look at another example. The probability of rolling an even number on a die and choosing a face card in a deck of cards. This may be a little bit harder to draw with a tree diagram, so we have to use that the probability of A and B is equal to the probability of A times the probability of B. So we have the probability of getting an even and a face card is the probability of getting an even number times the probability of getting a face card. The probability of getting an even is 1/2. The probability of getting a face card, is 3/13, which equals 3/26. It's 3/13 since there are 12 cards in a deck of 52, which would reduce to 3/13. Let's have a look at an example. You may want to pause the clip, try the example on your own. I will continue with the solution. What is the probability of selecting an ace and then selecting a diamond if the first card is replaced? This gives us the indication that these 2 events are independent because the first card is replaced. The probability of selecting an ace, well, in a deck of 52 playing cards, there are 4 aces over the 52, which is equal to 1/13. The probability of getting a diamond, there are 13 diamonds out of 52 cards, which is equal to 1/4. So the probability of getting an ace and a diamond, the probability of getting an ace and a diamond is equal to 1/13 times 1/4, which is equal to 1/52. Once again, you may want to pause the clip right now and attempt this example on your own. I'm going to continue with the solution. A 6-sided die is rolled twice. What is the probability of getting a 3 and then getting an even number? So the probability of getting a 3 will be 1 over 6 times the probability of getting an even number will be 1/2, which will give us 1/12. So in summary, the probability of event A, of course, is the number of favorable outcomes to A over the total number of possible outcomes. If two events are independent, then the probability of event B does not depend on the probability of event A occurring. The probability of two independent events occurring, the probability of A and B, is the probability of A multiplied by the probability of B.